Hi, I'm Gouri Krishnan, a junior from King's School, and today I'll be doing my presentation on electrochromism with titanium chromium oxide on silicon iridium and FTO, or fluorine-doped tin oxide, as well as how I used FDTD, or finite difference time domain computer modeling, to simulate the color changes which occur when metal oxides are grown on multiple different substrates. With more than 60% of energy used for electricity generation lost during the process, the issue of how to save energy has come to the forefront of research in recent years, particularly as greenhouse gas emissions from wasted energy continue to increase the effects of global warming and climate change at a rapid and unacceptable pace. Unfortunately, this is not a simple problem to solve, as many research studies have shown that there are multiple issues with the energy production process. Many different solutions have been tested to ameliorate this problem, but in particular, energy-saving electrochromic windows have been touted as one of the most promising solutions in recent years. So what are electrochromic windows? Electrochromic windows, shown here in this image, or electrochromic materials more specifically, are materials which are able to exhibit a color change after undergoing an electrochemical reaction. This color change occurs due to a shift in the reflectance and transmittance spectrums of a material after an electrochemically induced reduction oxidation or redox reaction. With this project, we aim to improve existing electrochromic windows by designing a more efficient electrochromic coating that can undergo a reversible color change when exposed to smaller magnitudes of positive and negative applied potentials. To achieve this goal, we utilize both in-person lab experimentation, the setup shown here to the left, as well as FDTD, or finite difference time domain modeling. Shown here to the right is an example of a model which has been constructed using FDTD modeling. FDTD modeling is a powerful modeling tool which has been used to successfully model optical device simulations on the nanoscale level in the cutting-edge fields of cancer research and computer science. This multifaceted approach not only allows for the development of an actual electrochromic layer, but also lends credibility to the aforementioned experimental results by modeling numerous scenarios to ensure that the layer will be effective at reducing energy emissions caused by the absorption of UV light. For the electrochromic layer, we aim to identify the most ideal combination of materials that would undergo a noticeable color change in a reasonable amount of time. Subsequently, we sought to determine if FDTD modeling could be used to accurately predict the color change that was supposed to occur. This would not only lend credibility to experimental results, but would also allow us to save on both time and resources, both of which were unfortunately scarce due to COVID-19. For our in-person experimentation, again, the setup shown here to the left, 3 separate designs for the original working electrochromic layer were tested, with the performance of titanium chromium oxide on silicon iridium on FTO, or fluorine-doped tin oxide, and ITO, or indium-doped tin oxide, being observed, though only the first 2 of these were deemed successful enough to attempt modeling simulations with. Our titanium chromium oxide thin film of 155 nanometers was grown on each of the 3 substrates using ALD, or atomic layer deposition, to ensure even thickness and conformity of thin film to substrate. After the growth of thin film, we subjected each sample to an applied electric potential, starting with a voltage of -3 volts. If no color change was observed, we increased potential by half a volt and repeated the observation process. This was done until a maximum of 3 volts of potential was reached. Our experimentation provided extremely promising results. As you can see in the figure to the left, indicated by the green arrow, a color change from clear to dark blue was achieved with the application of 2.5 volts of electric potential to titanium chromium oxide thin film grown on silicon iridium. The figure to the right shows another extremely promising color change, from tan to dark purple, which was achieved after 3 volts was applied over 75 minutes to titanium chromium oxide thin film grown on FTO. I'll explain the significance of this color change a little later in my presentation. If a color change was observed, numerical FDTD software was used to build multi-layer models resembling the previously mentioned samples in order to see if a color change could be replicated through modeling. The properties of each layer of material were set with sets of optical constants, also known as NK data, which were extracted from complete ease ellipsometry software. Before I explain the model, I'll give a quick explanation of a property which was central to the results of the modeling, the NK data. N and K are 2 complex refractive indices which determine how light interacts with the material. N is the refractive index, which measures how much the light changes directions when it hits the material, and K is the extinction coefficient, which is a measure of how strongly the substance absorbs light at a given wavelength. These two datasets here are the N and K datasets we use for iridium and titanium chromium oxide, shown to the left and right respectively. We use these in our experimentation, and as you can see, as the wavelength increases, the values for N and K vary. We built two models, one modeling titanium chromium oxide on silicon iridium, shown to the left, and one modeling titanium chromium oxide, or FTO, on FTO, shown to the right. As you can see, the model to the left was built as a two-layer structure. The top layer, or the lavender layer, was a titanium chromium oxide layer with a thickness of 155 nanometers, and the bottom layer, or silver layer, was an iridium layer with a thickness of 50 nanometers. For the model to the right, we decided to build it as a two-layer structure. The top layer, or the purple layer, was titanium chromium oxide with a thickness of 176 nanometers, and the bottom layer, or the tan layer, was fluorine-doped tin oxide with a thickness of 600 nanometers. Each model was then exposed to a plane wave light source within a range of 300 to 800 nanometers to simulate the effects of visible light on the model. This is represented in the bottom right corner by the downwards pointing purple arrow. As part of the model, we also added two frequency domain field and power monitors, which would capture the TR, or transmittance reflectance data, and plot a spectrum of the values. Similarly to our experimental results, we achieved promising results through our use of computer modeling. This is a reflectance spectrum generated by running FDTD modeling on the FTO model. As you can see, the graph has multiple reflectance spectrums. For each simulation, as I mentioned earlier, the properties of materials were set with NK datasets for before and after the reaction, resulting in two sets of reflectance spectrums. However, through ellipsometry fitting, we obtained four different sets of NK datasets for after the reaction. Since our goal was to obtain the best fit between the measured and simulated reflectance spectrums, I decided to graph all reflectance spectrums produced by different NK datasets in order to compare them with each other and the measured experimental reflectance. Our results show that dataset 1, shown here in blue, produced the closest fit with experimental data. Notably, we also improved on previous attempts at modeling. The graph on the left shows the previous attempt, and the graph to the right shows the current attempt. The graph plots the reflectance percent on the y-axis and the wavelength in nanometers on the x-axis. You can see the peaks of reflection on both graphs. However, the peaks on the graph to the left have been indicated with black and red dashed lines, as they are not as well defined as the peaks on the graph to the right. The reason why we aimed to focus on the peak values was because the peak locations often determine the overall shape of the reflectance curve. Since it may be hard to observe the improvement and fit visually side by side, I've also organized the results in a tabular form, which has been shown on the next slide. Here are the results in a tabular form. I'll start with the reflectance spectrum generated for the before reaction data. The top table shows the results of the previous simulation, while the bottom one is the results of the simulation which I ran. Our experimentation provided us with three reflectance peak values, shown here in the third column, indicated by peak position from UV-Vis. We also obtained three peaks from our modeling, indicated by peak position from modeling, and our goal with the simulations was to try and obtain the smallest difference between the experimental peak values and reflected peak values from the simulations. Our reasoning for this was that a close fit between experimentally produced and modeled reflectance spectrums indicated a model setup which mimicked the in-person experimentation closely, allowing for modeling results which more accurately match the experimental ones. As you can see, we obtained differences of 5, 3, and 40 nanometers from our previous modeling. Although 5 and 3 nanometers are relatively small differences, the difference of 40 nanometers was too large to expect successful results when modeling. Therefore, our main goal was to reduce this difference. I was able to reduce this difference to 30 nanometers through my modeling. However, this did come with a slight drawback of small increases to 11 and 4 nanometers for peaks 1 and 2 respectively. We took a similar approach for the titanium chromium oxide grown on FTO after the reaction. However, this result was extremely promising since we were able to reduce the difference from 11, 5, and 23 nanometers to 8, -1, and 19 nanometers, a decrease in differences for all three peaks. The simulated spectra were then entered into a website which predicted the color change that would occur. Notably, for FTO, the website predicted a color change to dark purple, which was also achieved through in-person experimentation. If you recall earlier in my presentation, I mentioned an experimental color change to dark purple, and here's the picture to remind you of that. So why is this color change significant? This color change signals the development of a successful electrochromic layer, which can help reduce the high amount of energy consumed during the cooling and heating phases. In fact, up to 14.9% of all energy is used in the cooling process. One application of an electrochromic layer, as I mentioned earlier, is its incorporation into window glass, which can then be used in industrial settings to reduce heating and cooling costs. In the winter, darkening the window allows for more light and heat to be absorbed, reducing heating costs. In the summer, lightening the window means less heat is absorbed, keeping cooling costs low. The color change depends only on the voltage applied. To allow for an individual user experience, apps have been designed which lets users control the amount of voltage, allowing them to customize their window settings for maximum comfort. In 2019, US facilities consumed over 36 quadrillion British thermal units of energy to produce only 14 quads of electricity. On a larger scale, as fuel is consumed for energy generation, carbon emissions rise, which in turn rapidly increases the rate of global warming. However, by incorporating the electrochromic material I described in this project into window glass, buildings and houses will be better able to resist heating up when the summer sun beams in. This in turn will allow us to reduce the use of devices which consume energy and give off carbon emissions, a prominent example being ACs. Additionally, this scaled-up method of energy loss reduction has the potential to replace oil, methane, and coal fuel sources entirely, hastening the process of shifting away from fossil fuels towards more efficient sources of energy. I'd like to thank Dr. Victoria Shellman and my lab mentor, Dr. Shu Hu, for their help and guidance, without which I would not have been able to co-author a paper on this project currently under review for publication in the Advanced Functional Materials Journal. Thank you for listening, and I'm now open to any questions.